Some steam locomotives were so disastrous they practically begged to be forgotten. From boilers that could not keep up with their own cylinders to cabs that cooked crews alive, these machines represent engineering ambition colliding with reality. Today, we are counting down the 20 worst old steam locomotives that faded into history. The Swiss Federal Railway's experimental C68 electric steam hybrid of 1926 sounded revolutionary on paper. Why not combine the best of both worlds? Swiss engineers attempted to mate a steam boiler with electric traction motors, creating a machine that promised the flexibility of steam and the efficiency of electricity. The reality was a maintenance nightmare wrapped in an engineering puzzle. The boiler produced steam to drive a generator that powered electric motors, which meant you had all the complexity of a steam locomotive and all the complexity of an electric one. Crews needed training in both systems. When something broke, and something always broke, technicians had to diagnose whether the problem was steam side or electric side. Often it was both. The locomotive spent more time in the shops than on the rails. Switzerland's tight tunnels and steep grades demanded reliability above all else. The CE68 hybrid delivered precisely the opposite. After barely 5 years of frustrating service punctuated by endless repairs, the Swiss quietly converted it to pure electric operation. The steam components were stripped out, and the experiment was never mentioned again. Sometimes combining two good ideas creates one bad one. The Soviet Union's AA-20 of 1934 embodied ambition pushed to absurd extremes. Soviet planners demanded the most powerful locomotive on Earth, and designers delivered something that looked like two locomotives welded together, because that is essentially what it was. The AA-20 stretched over 108 feet, with two complete boiler and firebox assemblies sharing a single frame. Double. The boilers meant double the power in theory. In practice, two fireboxes meant two firemen shoveling coal constantly, and two boilers meant twice the maintenance. The articulated frame twisted and flexed on curves in ways designers had not predicted. Steam joints leaked continuously. The pistons could not synchronize properly, causing the massive machine to lurch and buck like an angry bull. Track damage was severe enough that some sections required replacement after the AA-20 passed through. Soviet engineers discovered there are physical limits to how long a rigid steam locomotive can be, and the AA-20 exceeded every one of them. Only one was built. It spent most of its brief existence being repaired, and it was scrapped within a decade. The Soviets learned their lesson and never attempted anything similar again. When LNER Chief Engineer Nigel Gresley unveiled locomotive number 10,000 in 1929, it was shrouded in such secrecy that workers called it the Hush Hush. Beneath its bulging streamlined shell lurked the boldest experiment in British railway history. It used a marine-style water tube boiler that operated at 450 pounds per square inch, nearly triple normal pressure. The promise was revolutionary. The reality was heartbreak. What worked beautifully on ships proved disastrous on rails. A locomotive endures constant vibration, jarring impacts, and temperature swings that ships never experience. The delicate tubes worked loose constantly. Air leaked into the sealed system, destroying efficiency. Scaling clogged the narrow passages. Maintenance crews spent hours tightening connections that would shake loose within days. The locomotive could not match the performance of ordinary A1 Pacifics, despite consuming more coal. Test runs became exercises in frustration as crews battled foaming, leaking, and inadequate steam. LNER engineers made modification after modification, but the fundamental problem remained. Marine technology simply did not translate to railway service. By 1936, they rebuilt it with a conventional boiler, erasing the experiment entirely. The London Midland Scottish Railway locomotive number 6399, Fury, carried a name that proved grimly prophetic. Built in 1929 with an ultra-high-pressure Schmidt boiler operating at 900 pounds per square inch, it represented the cutting edge of steam technology. It also represented how that cutting edge could cut back. The compound expansion system was fiendishly complex, using high-pressure steam 3 separate times before exhausting it. In theory, this extracted maximum energy from every pound of coal. In practice, the intricate pipework created dozens of potential failure points. During a demonstration run in February 1930, one of the high-pressure drums ruptured catastrophically. The explosion killed a company director who had come to observe and scolded the fireman so severely he died from his injuries. It was one of the worst locomotive accidents in British history. The investigation revealed that the sophisticated boiler technology demanded maintenance standards essentially impossible to achieve in regular service. The Fury sat in the works for over 5 years, while LMS debated what to do. Eventually, they rebuilt it with a conventional boiler, renamed it British Legion, and pretended the experiment never happened. When the Chesapeake and Ohio Railway unveiled its M1 steam turbine locomotives in 1947, they called them the future of railroading. Crews quickly renamed them sacred cows because of their enormous expense and need for constant pampering. These 154-foot behemoths were the longest steam locomotives ever built, stretching so far they could not fit on most turntables. Not one of the 3 M1s ever completed a single trip from Washington to Cincinnati without breaking down. Not one. The design placed a coal bunker at the front, a boiler facing backward, and a steam turbine driving electric generators that powered traction motors. Coal dust and water constantly infiltrated the electrical equipment, causing short circuits and motor failures. The turbines consumed astronomical amounts of coal and water at low speeds, negating any efficiency gains from the turbine technology. Intended to power the luxurious chassis streamliner, the M1s never hauled a single revenue passenger. The train was cancelled before it launched, leaving these enormously expensive machines without purpose. After just 3 years of frustrating trials between Clifton Forge and Charlottesville, all 3 were scrapped in 1950. The Pennsylvania Railroad's T1 duplex looked like the future of steam when it debuted in 1942. Its sleek Raymond Loewy styling concealed an innovative duplex drive system with 2 pairs of cylinders. The Pennsylvania Railroad built 52 of them, betting heavily that this design would outperform diesels. They bet wrong. The T1 locomotives were blindingly fast, capable of exceeding 100 miles per hour with ease. They were also dangerously prone to wheel slip. The duplex arrangement divided the driving force between 2 smaller engine units, reducing the weight on each set of drivers. When one set started slipping, the other would follow instantly. Engineers reported terrifying moments when all 8 drivers would suddenly lose traction at high speed, sending the locomotive into violent oscillations. The poppet valves that were supposed to improve efficiency proved maintenance nightmares, requiring constant adjustment. The locomotives consumed fuel and water at rates that horrified accountants. Most critically, they proved less reliable than the diesels they were supposed to defeat. By 1953, just 7 years after the last was built, every T1 had been scrapped. The Pennsylvania Railroad's gamble on advanced steam technology had failed completely. Baldwin Locomotive Works named their first triplex locomotive Matt H. Shea, after a beloved Erie Railroad employee. The 1914 Behemoth deserved a more cautionary name. This 28882 monster packed 24 driving wheels, powered by 6 massive cylinders arranged in 3 sets of 8. It generated 160,000 pounds of tractive effort, more than any locomotive before or since. It also could not move faster than a brisk walking pace. The problem was physics. 6 cylinders demanded enormous quantities of steam, far more than even the Matt H. Shea's oversized boiler could produce. Above 10 miles per hour, steam pressure collapsed and the locomotive stalled. Crews nicknamed it the Yard Ripper because while it could drag impossibly heavy trains out of terminals, it could not actually take them anywhere. The 3rd set of drivers sat under the tender, and as coal and water were consumed, the tender lightened and those drivers lost traction. Making matters worse, the rear engine unit could not generate proper exhaust draft to help fire the boiler. Erie built 3 triplexes, and the Virginian Railway tried 1. all proved useless for mainline service. By 1933, every triplex was scrapped. Oliver Bulleid's Leader class represented steam locomotive design at its most delusional. When it emerged from Brighton Works in 1949, this bizarre 060 plus 060 looked more like a diesel than any steam locomotive. That was intentional. Bulleid believed steam could compete with diesels if it adopted diesel-like characteristics. Every innovation proved disastrous. The fully enclosed design trapped heat inside, turning the fireman's central compartment into a literal oven. Temperatures exceeded 140 degrees Fahrenheit during operation. Flames from the firebox would enter the cab at high outputs, forcing crews to keep doors open just to survive. The sleeve valves that were supposed to reduce maintenance broke constantly, stranding the locomotive miles from help. The chain-driven valve gear proved equally troublesome. Water consumption was so extreme, the locomotive required frequent stops, and the height of the enclosed body meant most water cranes could not reach the filler cap. Of 5 leaders ordered, only 1 was completed. That one spent more time being towed back to the shops than actually running. By 1951, the entire project was cancelled and every component was scrapped. In 1938, General Electric built 2 steam turbine locomotives for Union Pacific that looked like nothing railroaders had ever seen. With their streamlined car bodies and a 2C plus C two-wheel arrangement, they resembled diesels, because that was essentially what they were, except they were powered by steam turbines instead of diesel engines. The concept made theoretical sense. Steam turbines worked brilliantly in ships. Why not trains? The locomotives toured the country, generating publicity and impressive test results, but actual service revealed fatal flaws. Steam turbines only operate efficiently at sustained high speeds. Freight railroading involves constant speed changes, stops, and starts. At low speeds, the turbines consumed horrifying amounts of fuel while producing minimal power. The complex condensing systems that worked fine in stationary installations proved impossible to maintain on moving locomotives. Coal dust wreaked havoc on precision turbine blades. After just 6 months of disappointing service, Union Pacific returned both locomotives to General Electric. By 1943, with World War II creating steel shortages, both were scrapped. They had run barely enough miles to justify their construction costs. The Camelback locomotive earned its name from its distinctive silhouette, with the engineer's cab perched awkwardly atop the boiler like a saddle on a camel's back. This strange arrangement was not a stylistic choice, but a desperate solution to an engineering problem. The massive Wootton firebox, designed to burn cheap anthracite waste called culm, was so wide it could not fit behind a conventional cab. Designers moved the cab forward, splitting the crew between 2 locations. The engineer sat isolated above the boiler, while the fireman stood exposed on a tiny platform at the rear. Communication between them was reduced to whistle signals and hope. Safety concerns were staggering. The engineer perched directly above the connecting rods. If one broke, and they did break, flying metal could kill him instantly. Railroaders grimly nicknamed these locomotives snappers for that reason. The Baltimore and Ohio reported twice the accident rate for Camelback crews compared to conventional locomotives. Heat from the boiler made the cab unbearably hot. Visibility was compromised in both directions. The Interstate Commerce Commission eventually banned new construction in 1927, but thousands had already been built. In 1861, engineer John Fowler faced an impossible problem. The Metropolitan Railway in London would run through tunnels where smoke could suffocate passengers. His solution was a fireless locomotive, storing heat in bricks instead of burning coal. The concept sounded ingenious. The reality was, nearly killed everyone. Fowler's creation packed a combustion chamber with fire bricks that would retain heat to generate steam through tunnels. The first trial on the Great Western Railway ran for 7.5 miles before disaster struck. The condensing system leaked, draining water from the boiler. Steam pressure plummeted and the feed pumps jammed. Suddenly, The crew faced an imminent explosion with no way to dump the fire because the heat was trapped in bricks that could not be removed. They narrowly escaped catastrophe. A second trial in 1862 failed just as spectacularly. The locomotive produced almost no steam. Fowler was so embarrassed he denied the engine existed. It sat sheeted up and hidden until sold in 1865. Railway historians dubbed it Fowler's ghost because for decades its creator refused to admit it was real. The locomotive was quietly scrapped in 1895, its existence an embarrassment. The Pennsylvania Railroad Q1 of 1942 was supposed to revolutionize freight hauling. Instead, it became a textbook example of how not to arrange cylinders. This 4-6-4 four-wheel arrangement duplex placed its rear cylinders facing backward, directly beneath the firebox. The designers forgot that fireboxes generate intense heat, ash, and soot. The backward-facing cylinders suffered constantly from that hellish environment. Heat warped components. Ash infiltrated bearings. The confined space meant neither the firebox nor the cylinders could be properly sized, and each constrained the other, compromising both. The steam pipes required to reach those rear cylinders were so long that significant power was lost before steam even reached the pistons. Engineers wrestled with a machine that fought them at every turn. During its short career, the Q1 spent more time in shops than on the rails, accumulating 165,000 miles before retirement. The Pennsylvania learned its lesson and moved the cylinders forward on the subsequent Q2 class. But the Q1 legacy was clear. Some ideas looked brilliant on paper and disastrous in practice. Mounting cylinders next to a roaring firebox fell into the latter category. The Q1 was scrapped in 1952, largely forgotten. The Pennsylvania Railroad's S1 was designed to be the ultimate passenger locomotive. What emerged in 1939 was so enormous it could barely fit on the railroad that ordered it. Measuring over 140 feet long and weighing over 1 million pounds with its tender, this 6446 duplex was possibly the largest passenger steam locomotive ever built. It was also, essentially, useless. The S1's massive size meant it could only operate on 283 miles of the Pennsylvania Railroad's vast network between Chicago and Crestline. Everywhere else, curves were too tight, turntables too small, infrastructure inadequate for this behemoth. Even on its limited territory, the S1 proved troublesome. The duplex arrangement created notorious wheel slip problems. At high speeds, violent surging would shake the entire machine. Engineers called it the big engine, with a mixture of awe and frustration. It could hit 100 miles per hour, certainly, but keeping it there required considerable skill, luck, and prayers. The Pennsylvania Railroad exhibited it at the 1939 World's Fair, where crowds marveled at its streamlined Raymond Loewy styling. What they did not see were maintenance crews struggling to keep it operational. By 1946, the S1 was withdrawn. Too big, too temperamental, too limited. South Africa's Class 25 condensing locomotives of 1953 represented engineering ambition confronting desert reality. The Karoo offered no water for hundreds of miles, making conventional steam operation impossible. So South African Railways created locomotives that recycled exhaust steam back into water. The condensing tender was a marvel of complexity. 6 steam-driven fans cooled exhaust through over 2 miles of radiator tubing, recovering 90% of water. On paper, these locomotives could travel 700 miles between water stops. In practice, they became nightmares. The radiator tubes clogged constantly with scale and deposits. Those 6 fans required constant attention. The condensing process raised back pressure on cylinders, reducing power. Crews had to balance speed against efficiency, a calculation that changed with every temperature variation. When temperatures rose, condensers struggled to cool steam adequately. Each locomotive required specialized maintenance that regular shops could not provide. Complexity meant breakdowns far from help. By the 1970s, diesels had proven far simpler for desert operations. The condensing Class 25 locomotives were retired, their brilliant engineering defeated by the reality that sometimes the clever solution is too clever by half. Baldwin and Westinghouse created the Pennsylvania Railroad S2 in 1944 with one goal: build a steam turbine that could outperform diesels. They succeeded brilliantly above 40 miles per hour. Below that speed, the S2 was a disaster. The direct drive steam turbine was elegant in concept. Instead of pistons hammering back and forth, steam spun a turbine connected to the driving wheels through reduction gearing. At high speeds, the S2 was remarkably efficient, smooth and quiet. British engineer E.S. Cox reported maintaining 100 miles per hour for 12 minutes, but freight yards and station stops exposed the fatal flaw. Turbines hate low speeds. Below 40 miles per hour, the S2 consumed astronomical quantities of steam and coal while producing minimal power. Boiler pressure would collapse from 310 pounds per square inch to just 85 pounds per square inch. The firebox ran so hot from excessive fuel consumption that stay bolts would fracture. The S2 was assigned to premier passenger runs between Chicago and Crestline, where sustained high speeds played to its strengths. But every station stop devoured fuel at rates that horrified accountants. After just 103,000 miles, the S2 was withdrawn in 1949 and scrapped. The London, Midland and Scottish Railways Turbomotive of 1935 was British engineering at its most ambitious. Locomotive 6202 looked like a conventional Princess Royal Pacific, but beneath its casing lurked a different beast. Instead of cylinders and pistons, a Swedish-designed steam turbine drove the wheels through reduction gearing. For 15 years, the Turbomotive worked reasonably well. It logged over 400,000 miles hauling express passenger trains between London and Liverpool. At sustained high speeds, it proved more efficient than its piston-driven sisters. But the turbine's complexity eventually overwhelmed its advantages. The main turbine required perfect balance at high rotational speeds. Blade damage could cause catastrophic vibration. A separate reverse turbine added weight and complexity. Reduction gearing needed constant adjustment. When the turbine required major overhaul in 1949, the London, Midland and Scottish Railway calculated that replacement would cost 3 times more than simply converting it to conventional propulsion. So they did exactly that. The Turbomotive became Princess Anne, an ordinary Pacific. It served 3 more years before a tragic collision at Harrow and Wealdstone destroyed it. The turbine experiment was over, defeated by economics. The Armstrong Whitworth steam turbine locomotive of 1922 looked more like a factory on wheels than a railway engine. This British design used a rotary evaporative condenser so massive it dominated the locomotive's appearance. The concept was theoretically sound. Condense exhaust steam, return it to the boiler, and reduce water consumption dramatically. The execution was mechanically insane. The condenser required steam to pass through rotating tubes, which were simultaneously sprayed with water for cooling. The evaporating water carried away heat, while rotation was supposed to improve efficiency. In reality, the convoluted airflow path through the rotating assembly strangled efficiency instead of improving it. The apparatus added enormous weight while producing minimal benefit. The locomotive was dramatically overweight and underpowered. Test runs demonstrated it could not keep pace with conventional designs of similar size. The turbine struggled with variable railway loads. It was efficient only within a narrow speed range. Within a year of construction, the locomotive was returned to its builders. By 1923, it was scrapped. The Armstrong Whitworth demonstrated that adding complexity does not add capability. Sometimes it just adds weight and embarrassment. The first steam locomotive explosion in American railroad history happened on June 17, 1831, and it was entirely preventable. The best friend of Charleston had been America's first regularly scheduled steam railroad locomotive, a source of enormous pride for the South Carolina Railroad. Then a fireman, annoyed by the constant hissing of the safety valve, sat on it. The physics were simple and deadly. Steam pressure built with nowhere to escape. The boiler became a bomb. When it ruptured, the explosion scattered wreckage across the tracks and killed the fireman instantly. The engineer survived, badly scalded. The locomotive was completely destroyed. South Carolina Railroad rebuilt it, sensibly renaming it the Phoenix, and added a barrier car loaded with cotton bales between the locomotive and passenger cars. But the best friend's demise exposed a fundamental truth about early steam technology. These machines operated on the edge of catastrophe. Boiler explosions would plague railroads for decades. The best friend became a cautionary tale, proof that the same steam pressure that powered these miraculous machines could destroy them in an instant. All it took was one blocked safety valve. Norfolk and Western's John Henry was steam's last desperate gamble. Named after the legendary steel driver who raced a machine and died, this 1954 steam turbine was supposed to prove coal power could defeat diesel. The irony of that name became grimly apparent. At 161 feet, the John Henry was the longest steam locomotive ever built. Its coal-fired boiler fed a steam turbine that powered electric generators, which drove traction motors on all 16 wheels. It produced 175,000 pounds of starting tractive effort, more than Norfolk and Western's legendary Class A locomotives. On paper, magnificent. In service, heartbreak. The Babcock and Wilcox water tube boiler had automatic controls that constantly malfunctioned. Coal dust and water infiltrated the electric traction motors, causing short circuits. The feed water pump had to operate beyond specifications, and it ran to failure repeatedly. The locomotive could not fit on any turntables. Its complex controls took engineers weeks to master. After just 3 years, Norfolk and Western gave up. The company that had built its own steam locomotives for decades admitted defeat. On January 4, 1958, the John Henry was retired. Within 3 years, it was scrapped. Like its namesake, it had fought the machine and lost. What happens when brilliant engineers are given unlimited resources and zero supervision? The Pennsylvania Railroad discovered the answer with its duplex locomotives, and the price was extinction. Between 1940 and 1946, the Pennsylvania Railroad poured millions into developing duplex technology. The S1 was too big. The Q1 was fundamentally flawed. The T1 was dangerously unreliable. The Q2, despite being most successful, still cost 50% more to maintain than conventional locomotives. But the true catastrophe was not any single locomotive. It was the opportunity cost. While the Pennsylvania Railroad chased steam turbines and duplex dreams, competitors bought diesel locomotives by the hundreds. The New York Central modernized. The Santa Fe modernized. The Pennsylvania Railroad fell behind, trapped by massive investment in technology already obsolete. By 1957, every experimental steam locomotive was scrap metal. The railroad that pioneered American passenger service staggered toward bankruptcy, merging with New York Central in 1968. 2 years later, Penn Central collapsed in the largest corporate bankruptcy in American history until that time. The Pennsylvania Railroad's experiments did not cause that bankruptcy, but they symbolized a railroad so focused on engineering perfection, it forgot economic reality. And that's all, folks. These were the 20 worst steam locomotives that faded into history, each a monument to ambition exceeding reality. Subscribe for more updates. Here is another video selected for you. See you next time.